Okay, so 6.3, we're talking about arc length. So arc length, if we have some function, some curve, some f of x, um, and we're looking at the arc length from A to B, the arc length is actually the distance this curve travels from A to B. And if you think about this, um, it- what we're going to do is when we had the Riemann sum, we were looking at summing up a lot of little rectangles. What we're going to be doing for this is we're going to be summing up a lot of little line segments. So if we have like a line segment from here to here, we can think of this as being two things. This is a little delta x, this is a little delta y. And this right here is the distance d. Well, we know these are, because this is now a right triangle, these are connected via the Pythagorean theorem, and that d squared equals really delta x squared plus delta y squared, or d equals the square root of delta x squared plus delta y squared. And if we remember from u substitution, if we have y equals, even some f of x, um, we take the derivative of this dy or delta y before we take the limit of this would be f prime of x 10 times the derivative dx. So this right here, this little delta y, could be turned into this. That is d is the square root of delta x squared plus f prime of x delta x squared. And more to the point, because these both now have a delta x in common, a delta x squared, we could factor that out, and d is going to equal square root of 1 plus f prime x squared, and then this would be a delta x. Now on the limit, this turns into a dx, and we can think of this the actual length here. We take the limit as the width, or one of these little delta x's or delta y's go to 0. These little line segments get finer and finer. We get the true area, or not the true area, but the true arc length of that curve, not the approximation. We can think of this, if we're going from A to B, as the integral from A to B of the square root of 1 plus the derivative squared dx. Or if we're going from like C, that's not a C, now it's a C to D, that right there, we could slice this, we'd have little delta y's there. There, the length is going to be the integral from C to D, the square root of 1 plus g prime of y squared dy. So those, this is essentially how we're doing it. But this right here, both of these are really just using this notion of the distance function, the distance between 2 points, and taking the distance between those 2 points to basically go to 0 in the limit. And this is what we're doing. So this is distance formula. This is a one-dimensional object, like arc length is one dimension. If you could cut that piece of graph out and pull it straight, it would just be a line, and we can measure that line. Although we can't do that, that's kind of the notion that we have of those things. So that's another piece. Now I'm going to show you a couple examples, and then we're going to call it good. So if we're trying to find the length, find the length of the function y equals the natural log of x minus x squared over 8. 1 less than or equal to x less than or equal to 2. One thing I can tell you right now is that this is going to be defined to be the integral from 1 to 2 of the square root of. This is y is a function of x, so we're going to have 1 plus dy dx. We're going to take the derivative of y with respect to x squared dx. So here, there's a couple pieces. First thing we want to do is we want to take the derivative of this function. So dy dx, derivative of the natural log is 1 over x. Bring the 2 down using the power rule here. That's going to be 1/4 x. That's the derivative. Now, it's not just the derivative, it's the derivative squared. So if we square this, dy dx squared, it's going to be 1 over x minus 1/4 x squared, which really we think about foiling itself. 1 over x minus 1/4 x, and 1 over x minus 1/4 x. If we FOIL this thing out, dy dx squared, 1 over x over 1 over x, that's going to be 1 over x squared. The outside, 1 over x times negative 1/4 x. Those x's cancel, we get negative 1/4. The inside, same thing, negative times positive is negative. The x's cancel, so we get 1/4. So all told, the negative 1/4 and negative 1/4 give us a negative 1/2. And finally, last, negative times negative is a positive. The 1/4 multiplied together to get a 16th. And the x is multiplied together to get an x squared. Now, it's not that we really just wanted the derivative squared. It's we want 1 plus the derivative squared. So here, if we have dy dx squared plus 1, that's the net effect of adding 1 to this right here. So if we add 1 to this, that 1 minus 1/2 is positive 1/2. So 1 over x squared plus 1/2 plus 1 over 16x squared. That is going to be what's underneath this radical. That's going to be that quotient, that radical right there. So when we look at that, we want to be able to take the square root of this. And if you notice, like this right here, and if you notice this right here and this right here, the only thing different about this red expression and this yellow expression right here is that's a negative and that's a positive. So this would FOIL. We'd still have this. We'd still have this term. The difference is that would no longer be negative, be positive. So this thing actually factors dy dx squared plus 1 is going to be a 1 over x plus 1/4 x squared. So in the substitution of this integral, we can put that in there. We're substituting this in right there. So the integral from 1 to 2 of the square root of 1 over x plus 1/4 x squared dx. This square and square root take care of each other. So the integral 1 over, or integral from 1 to 2 of 1 over x plus 1/4 x dx. The antiderivative of this is going to be the natural log of the absolute value of x. This, when we add 1 divided by, we're going to have plus 1/8 x squared, evaluating that between 1 and 2, plugging our upper bound in, natural log of 2 plus 1/8 times 2 squared minus natural log of 1 plus 1/8 1 squared. And here the natural log of 2 is just the natural log of 2. This right here is going to be 4. So 2 squared is 4 times 1/8. I'm going to say that's 4/8. The natural log of 1 is 0. So that's going to be 0. And here 1/8 times 1 squared is going to be 1/8. So we're subtracting it off, minus 1/8. If we take the 8th away from these 4/8, we're going to have the natural log of 2, or the absolute value of 2, which is 2, plus 3/8. And that right there is what that is the length of this curve right here between 1 and 2. So we'll take a look at another one of these, and we're going to find the length of y equals x cubed over 3 plus 1 over 4x, and we have 1 less than or equal to x less than or equal to 3. So if we set up this integral, this is going to be the integral from 1 to 3 of the square root of y is a function of x, so we're going to have 1 plus dy dx squared, and we have a dx there. And we get our bounds right from that. That's given in the problem. Now, once again, we're going to have to do some things. We have to first take the derivative. So the derivative of this, if we write this as y equals 1/3 x to the third plus 1/4 x to the negative first power, we can use the power rule on this. So dy dx is going to be, bring the 3 down. So x squared, subtract 1. Bring this down, we're going to have negative 1/4. We subtract 1, x to the negative second. So that's the derivative. If we want to now square the derivative like we have in our formula, we're going to have dy dx squared, which is going to be x squared minus 1/4 x to the negative second squared, which is really just FOILing. X squared minus 1/4 x to the negative second times x squared minus 1/4 x to the negative second. So dy dx squared, x squared times x squared is x to the 4th. The outside, x squared times x to the negative 2, you add those exponents together and get x to the 0th. So 1 times 1/4, that's going to be a negative 1/4. The inside, same thing, x squared times x to the negative second, add the exponents, x to 0, another negative 1/4. We add those together, get negative 1/2. And finally, negative 1/4 and negative 1/4 is positive 1/16. X to the negative second times x to the negative second, add those exponents, and we get x to the negative fourth. Now, that's got us up to this point. We really want to add 1 to this. So if we add 1 to this, dy dx squared plus 1, if we add 1 to this, all we're doing is add that, which makes that a positive 1/2. So x to the fourth plus 1/2 plus 1/16 x to the negative fourth. And then notice that this and this are identical. The only difference between this is the sign of the 1/2, which means this is going to actually factor back into this thing with a plus. So x squared plus 1/4 x to the negative second. This is what is going to be underneath our integral. So here, if we have the integral from 1 to 3, this whole thing under the radical is this thing, squared. So we're going to have the square root of x squared plus 1/4 x to the negative second squared dx. The square and the square root take care of each other. So we have the integral from 1 to 3 of x squared plus 1/4 x to the negative second dx. Power rule, so add 1 and divide by this. So x to the third divided by 3. Add 1 to this and divide by this. It's going to be negative 1/4 x to the negative first. We're going to evaluate this between 1 and 3. And yeah, like if you're looking at this original thing and looking at this, they are quite similar. That because of the construction of this problem, they're going to come out a lot like that. But I'm going to go ahead and plug the upper bound in. So 3 cubed over 3 minus 1/4 times 3 to the negative first. Minus plugging 1 in, 1 cubed over 3 minus 1/4 1 to the negative first. 3 cubed is 27 divided by 3 is 9. Here, this would be a 1 over 3, so that's a 1/12 minus, here we're going to have what, 1/3 minus 1/4. So 1 cubed is 1, 1 to the negative 1 is 1. So this over here, we get common denominator, this would be 4/12 minus 3/12. So we have 9 minus 1/12 minus 1/12, which would be 9 minus 1/6, which 6 times 9 is 54 minus 1, we'd have 53/6. That'd be the improper fraction version of that, which I'm quite good with. Now, sometimes in my math lab, they're going to ask you just to set the problem up but do not solve. So here, if you have y equals tangent of x, we're trying to find the arc length that's between negative pi over 3 less than or equal x less than or equal 0. We still want to know, like this is in y is in terms of x, so we're going to have the integral from negative pi over 3 to 0. We still want to have the square root of 1 plus dy dx squared dx. We want to find dy dx, derivative of tangent secant squared x. If we square this, negative pi over 3, 0, the square root of 1 plus, squaring the square would be a secant to the fourth of x dx. We don't really know what the antiderivative of this is. We don't have the machinery or knowledge to do this right now. So just leave it there. This is the setup of how we would find the arc length of the tangent function from negative pi over 3 to 0. Okay. So the last one we're going to do is we're going to take the graph. We're going to take an equation, the graph of an equation called an asteroid, and it's x to the 2/3 power plus y to the 2/3 power equals 1. And what it looks like is it's like a diamond with curved interior pieces. So this one's concave up, that one's concave up, that one's concave down, that one's concave down. So it looks about like that. So we want to find the length of this. Now, what we can do is we can find the length of basically this right here. Because of symmetry, there's 1, 2, 3, 4, 5, 6, 7, 8. If we find this, the length of this piece right here, multiplied by 8, that is actually going to be the true length. So in this right here would be from where radical 2 over 4 is less than or equal to x, which is less than or equal to 1. And we can multiply this integral by 8. So here, if we have 8 times the integral from radical 2 over 4 to 1 of, now once again, because we're going to use this in terms of x, we want a dx over here, we need to solve this for y. So if we subtract that over, we're going to have y equals 1 minus, y to the 2/3. It's going to be 1 minus x to the 2/3. If we raise both sides to the reciprocal power, we have y equals 1 minus x to the 2/3 to the 3/2 power. Now, if we take the derivative of this, because we're going to square 1 plus dy dx squared, we want to take the derivative. So dy dx is going to be bring the 2/3, 3/2, down to 1 minus x to the 2/3. Subtract 1, that's going to be the 1/2 power. By the chain rule, we have to multiply this by the derivative of the inside. Derivative of 1 is 0. That's a constant. Derivative of negative x to the 2/3. Bring this down, negative 2/3 x to the, subtract 1 from this, negative 1/3 power. And that's the derivative. Now I'm going to clean this up a little bit. dy dx is going to be this negative multiplies by this, making a negative. This is a reciprocal, so the 3's and 2's, they cancel. This is a negative exponent, so I'm going to write this. This is a positive exponent, 1 minus x to the 2/3 to the 1/2 all over x to the 1/3. That's what that's going to be. Now, we need to get that squared. So if we square this, dy dx squared, it's going to be the same as squaring this, negative 1 minus x to the 2/3 power to the 1/2 power all over x to the 1/3 power squared. Squaring the negative, so dx squared. Squaring the negative is going to make it a positive. Squaring that 1/2 power, we multiply. So in the numerator, we get a 1 minus x to the 2/3. Raising the denominator to the squared power, we multiply x to the 2/3 power. Now, I'm going to write this a little bit differently. dy dx equals 1 over x to the 2/3 minus x to the 2/3 over x to the 2/3. So splitting this fraction up in the numerator right here into two pieces. So this is the derivative squared, dy dx squared is going to be this. We have 1 over x to the 2/3 minus 1. Now recall, to this we have to add 1. So when we add 1 to this, those cancel out. And this whole thing in here, we have 8 times the integral of radical 2 over 4 to 1. Those cancel out. We just have the square root of 1 over x to the 2/3 power dx. Square root of 1 is 1. So we have 8 times the integral radical 2 over 4 to 1 of square root of 1 is 1. The square root here is really multiplying by the 1/2 power. So we have x to the 1/3 dx, which I now copy this on the next page. So we have 8 integral from radical 2 over 4 to 1 of, really we have x to the negative 1/3 power dx. Adding 1, we're going to get 2/3. Dividing by 2/3, we have 3/2. So 8 times 3/2 x to the 2/3. And we're going to put on our upper bound, our lower bound. So the lower bound's radical 2 over 4, the upper bound 1. Here we get 4 times 3 is going to go as 12. 1 to the 2/3 power minus radical 2 over 4 to the 2/3 power. Now, anything 1 to any power is 1. So we're good with that. So then we're going to have 12 times 1. Really, when we see this as the radical 2 over 4 to the 2/3 power, I can square this. So that's going to give us 2 over 16, which is 1/8. The 1/3 power is the cube root of that, so that'd be 1/2. So the cube root of 1/8 is 1/2, because 1/2 times 1/2 times 1/2 is 1/8. 1 minus 1/2 is 1/2, so it's 12 times 1/2, which is 6 units. And that's the length of the total asteroid right here, going all the way around like that. So that's that. I know it's kind of quick. I think you guys are watching things in 1.5 speed anyway, but I don't know. Hopefully it worked for you. It's more formulaic. I think you're going to like it better than 6.1 and 6.2. That's it. Hope you're well.